Hello everybody, it's me again, and we were interrupted by some call, but everything is fine now. We start talking about NVIDIA Rubin GPU. It has increase in floating point 4 operations, which is short format of the numbers, and of course this is for the tensor cores, and it's 5 times more there than Blackwell microarchitecture. Also, in sense of training for the floating point operations and the shortened format of numbers FP4, and for the training it is 35 petaflops, which is 3.5 than more 3.5 times more than Blackwell, and here it's 50 petaflops. So this is the comparison of the capabilities of the Blackwell and the Rubin GPU architecture. New high bandwidth memory is used. It's a high bandwidth memory 4. They mentioned that they are preparing this for the manufacturing, but now it's obviously that they are using it in design. It enables 22 terabytes per second memory bandwidth between GPU and the CPU. And let's remember that we also have memory bandwidth between CPU and system memory. And you see that this is different kind of memory. The previous one was DDR, and here this is high bandwidth memory that has probably more lot more pins than classic memory in DDR format. Also, NVLink bandwidth per GPU. We mentioned this in previous when we talk about NVLink 6.0. It's 3.6. It's doubled in comparison with the Blackwell architecture, because there was 1.8 terabytes per second, and also number of transistors. It's 336 billions, which is 1.6 more. So we see that the basic things are at least doubled, but also significant increase in a tensor core. Tensor cores probably tensor core architecture is much better and improved in comparison with the Blackwell. And let's say Blackwell was probably very strong architecture. So we see at least 2 times increase in capabilities, and in some things it's 5 times more capabilities. And also we can see that increase was also achieved in CPUs and GPUs in parallel, at least 2 times. So every point is let's say doubled. So when you use in combination these two 1-2 punch, let's say Vera Rubin CPU GPU, you probably can achieve much more faster data flow and calculation. So, and we also can remember one important thing, and that is that NVIDIA is always going fast flow of data, and this as much as possible distribute data calculations and things you do. So that's their, let's say, philosophy, to don't every bottleneck of the jamming of the data or calculation must be erased and must be increased, and they are, let's say, trying to reach this Moore's law with these points, that number of things must be doubled in the new year's next generation. So they put a lot of effort to achieve some things and to be number one in the market. Okay, then we can continue and see what is the combination of these things on a board. This is probably one lattice or one node which is doing calculation, and we can see combo of one Vera CPU and two Rubin GPUs, and also I'm not quite sure is this NVLinks are closest is this NVLink a port for these GPUs or switch? I think switch is probably somewhere else on a special node as it was in previous design. But this is probably the port with the 18 links generation NVLink 6. And also you can see two Rubin GPUs. And we will see how it's connected with this Vera CPU through the chip-to-chip NVLink connection. Here is present NVLink chip. I'm assuming that this all around is probably high bandwidth memory. And we will see it's supposed to be 288 gigabytes per GPU. So two GPUs means double that, 288 gigabytes gigabytes. And also we can see that LPDDR5X, so probably this is the type of connection. It's all around this Vera CPU. And also on the other side, we have classical PCI connection generation 6. So NVLink on one side and PCIe generation 6 on the other side. So as you can see, flow. Full the memory, high bandwidth, the high data flow, also full the memory, high bandwidth and data flow, distribute to many cores, distribute. So we have that philosophy of good flow, very fast flow, and then when you flow, have large storage, and from that storage with the high memory bandwidth, and for the CPU and for the GPU, you optimize feeding of the device which are doing calculation, and then inside the architecture with so many cores here, and here, you optimize even doing the process of the calculation. So I think everybody can see the obvious philosophy of NVIDIA design to have optimized and fast and distributed operations as much as possible. And even it has two sides of data flow. So this side is coming from the NVLink switch, which we mentioned as a third chip. And here we have PCI generation 6, which is of the classical communication like for the CPU. It has so many ways to receive data. So the thing what is meant to be this design is obvious by this NVLinks and PCIe ports. Also, NVIDIA Vera Rubin Superchip, they call it Superchip. This one, a CPU, and these two GPUs, they call it Superchip, and we will see how they are connected. They are so close, you can consider it as a one Superchip, CPU, GPU, or Vera Rubin Superchip. And then probably for this one tray, it has 100 petaflops I compute power, Now, repeating the things, 88 NVIDIA custom Olympus CPU cores and 2 terabytes of fast memory. Probably this is high bandwidth memory, but we will see later. Maybe this is in total, but I'm not sure. Or this is in total when you add GPU and CPU memory, but we will see. It is close to this because if we have LPDDR5X 1.5 terabytes, and for these two CPUs 288 gigabytes. When you add this and double this, it's almost 500 gigabytes. So in total, for this unit, it's 2 terabytes of memory in total. But we will see. I'm just assuming that's the case. Let's see how they are connected. So they call it Superchip because we have one CPU and two GPU chips. This is Vera CPU, and it was mentioned that it has 88 cores, and these are GPU units with capability of to be attached up to 288 gigabytes high bandwidth memory 4. We saw that small units. And we have two of them, and when you add here and here this GPU memories, you have more than 500 gigabytes, and when you add up this 1.5 terabytes, you have more than 2 terabytes of total memory. What is the new thing to be seen here? It is 1.2 terabytes per second memory bandwidth for the between CPU or system memory and the Vera GPU. And in previous case, it was I think 480 gigabytes per second. So it's more than I think doubled. Connection of Vera CPU with the other devices, which can transfer some data and achieve data flow towards this CPU, is through the PCIe Generation 6. We saw that there is two ports, I think, for the PCI. We can go one slide back. Actually, it seems like 3 ports, but it's not that important. We are not, let's say, we cannot gain data about exact design, but probably maybe this is two-sided PCI Generation 6, so maybe 2 ports, which enables the data flow towards other devices through some other network, probably elements and all chips that we are mentioned previously. And now we said that in comparison to the Grace CPU, we have NVLink chip-to-chip, which is doubled. There was 900 gigabytes per second bandwidth for chip-to-chip communication. Now it's doubled, so probably 900 is going towards one Rubin GPU and another 900 gigabytes per second going towards other. Also, memory bandwidth for this Rubin GPUs is 22 terabytes in comparison with the previous design of the Blackwell architecture, which has 8 terabytes per second. And I think on a Hopper GPU architecture, it was from 4 to 4.8 terabytes per second. So we see that memory bandwidth for the GPUs is also increasing, and let's say we can freely say that it is doubling. So that's for the Superchip. We see that And here is not symbolically represented that we have NVLink ports for each, which enabling 3.6 terabytes um, bandwidth through the NVLink, which is not shown here, which has nothing to do with these mentioned here, but it's let's say side side connection for the GPU. It has two-way connection chip to chip, and also through the NVLink port on it, which going towards NVLink switches, and the NVLink switches are inside a special let's say tray or node, which consists of two, probably I'm guessing two NVLink switches. So that's it for the basics of this design. Um, we see the philosophy and how they did it and how they achieved some things. This architecture of the superchip is changing. It was in first case it was Grace Hopper, so one Grace CPU and Hopper GPU. But sometimes in that case maybe there was connection and shared they shared this NVLink chip to chip. We see that NVIDIA is using these efficient NVLink connections and in chip to chip form and to classical NVLink form, because they one order of magnitude, let's say, higher than classical PCIe communication, even for the generation 6. So they are achieving good data flow with their special, let's say, way of connecting the chips than it was case with the PCIe. So that's it for this first intro of NVIDIA newest design, and soon you can expect more things similar with the content. And if they show some Rubin GPU architecture, I'm almost more than ready to present it to you in some likable way, I hope. So greetings for now, and see you later.